Specifications of multimeter and their significance. Multimeter components display. Shows numerical readings in units. Range button. Changes the measurement range manually. Power. Turns the device on or off. Selector switch. Dial used to choose measurement modes. Input jacks. Ports where test leads plug in. Probes. Red and black test leads for measuring circuits. Technical core specifications. Basic measurements. Voltage, V, measures potential difference in both DC and AC circuits. Current, A, measures electron flow in amperes. Resistance, omega, measures opposition to current flow. Specialized modes. Capacitance, F, tests energy storage capacity. Continuity, provides an audible check for a complete circuit path. Frequency, HC, measures the signal oscillation rate. Resolution is the smallest change in an electrical signal that a digital multimeter can detect and display, directly tied to the number of display counts, such as 6,000 counts. Key concepts. Smallest change represents the minimum increment the meter can register on a given range. Display counts. Higher counts, like 6,000 vs 2,000, allow the meter to show finer decimal precision and smaller signal changes. Practical impact. Essential in low-voltage electronics where a minor shift like 0.01 volts changes the diagnosis. Accuracy and precision in measurement quality. Core definitions. Accuracy. How close a measured value is to the true or actual value. Precision. How consistent and repeatable measurements are when taken under the same conditions. Key takeaway. Independence. A measurement tool can be highly precise, giving the exact same result repeatedly. Without being accurate, the result is far from the true value. Visual representation. The graph shows a normal distribution curve representing a measurement profile. Measured value. The center peak shows the most frequent measurement result. Confidence interval. The dashed line represents a 95% measurement confidence range. Boundaries. The solid red vertical lines mark the possible lower value and possible upper value within that confidence limit. Understanding input impedance, Z_. Input impedance is the opposition a circuit presents to an alternating or direct current flowing into it from an external source. For digital multimeters, DMMs, and measuring instruments, a high input impedance is critical for accurate measurements. Key concepts from the slide. Standard specification. 10, text, M, omega, 10, text, million ohms, is the standard value for most high-quality digital multimeters. Minimizing loading effect. High impedance prevents the meter from drawing significant current from the circuit under test, preserving the original circuit conditions. Error prevention. Low impedance meters draw too much current, dropping the voltage across the circuit's internal resistance and causing false low voltage readings. Significance. Crucial for testing delicate systems like automotive sensors, microcontrollers, and computer control modules. True RMS meters provide accurate AC voltage and current readings regardless of whether the waveform is a perfect sine wave or highly distorted. Key differences. Average sensing meters. These assume a perfect, clean sine wave. They measure the average AC value and multiply it by 1.11 to display the root mean square, RMS. If the wave is distorted, like the red dashed line, the reading will be highly inaccurate. True RMS meters. These use internal electronics to mathematically calculate the actual heating value of the waveform. This ensures precise measurements for both perfect sine waves, blue line, and irregular, non-sinusoidal waves, red dashed line. The image compares manual and auto-ranging digital multimeters, highlighting how manual ranging requires you to select the measurement magnitude while auto-ranging automatically detects signal strength and prevents overload errors. Manual ranging. You pick the range value. It responds fast on repeated tests but needs prior knowledge of expected values. Auto-ranging. The meter chooses the range automatically. It is safer and ideal when testing unknown signal levels. If you would like, I can explain how to choose the correct range manually or give tips on reading multimeter symbols. CAT, category, ratings define electrical safety measurement categories under IEC 61010-1, classifying environments by their potential to withstand voltage transients, spikes, and energy levels. Higher categories indicate closer proximity to the power source with higher available fault currents. Breakdown of CAT ratings. CAT I, protected low-voltage electronic circuits, signal levels, and equipment not directly connected to mains power, e.g., secondary copier electronics, protected board levels. CAT II, single-phase local receptacle loads and plug-in appliances, e.g., televisions, portable tools, household outlets. The image outlines 3 key dynamic performance metrics for digital multimeters or electrical testing meters: burden voltage, update speed, and min/max hold. Key metrics explained: burden voltage. The voltage drop across the meter when measuring current. High burden voltage can alter or disrupt the behavior of sensitive low-voltage circuits. Update speed. The number of times per second the display refreshes its reading, which is essential for capturing fast, transient changes in a live signal. Min/max hold. A function that records and displays the highest and lowest recorded measurements over a set period to catch intermittent voltage drops or spikes.